Lesson 10 is polynomial identities, and the first two sections of lesson 10 are just kind of proving them. So just to save you guys like kind of time in watching the video, I just put the proofs down there and then I'm going to kind of explain each step. I think it'll go a lot faster than if I was like kind of writing all the reasons as well. So example 1 from 10.1, this is proving the like kind of difference of squares pattern that we talked about in factoring before. So given a plus b times a minus b, we just want to prove like why it ends up at a squared minus b squared, which is like, you know, when we factor, we like start down here and we end up here. So the first step in proving it is using the distributive property. So we're taking a and we're distributing it to the second parentheses, and then we're taking b and distributing it to the second parentheses, and that's what they did in step 2. So they have a times that parentheses, and then b times that parentheses, and then after that we use the distributive property again. So we would do a times a, which is how we end up at this a squared, a times negative b, which is how we end up at that minus ab, and then over here we distribute the b times a plus ba, b times negative b minus b squared. And then after that, I know that this is like a BA and this is an AB, but we can use the commutative property to just go ahead and switch this term around. The commutative property is like, you know, if things are being multiplied, if there's a bunch of factors, we can reorder those factors and it's totally fine. So we switch this BA into an AB, and then from there we go ahead and simplify by combining like terms. So minus AB and plus AB, those two are like terms. They're the same term, they just one is positive, one is negative, so they wipe each other out. And that leaves us with just a squared minus b squared, which is what we are trying to prove. Okay, so example 2 is proving the like one of the perfect square trinomial patterns. So we're trying to start with a minus b squared and prove that we end up with a squared minus 2ab plus b squared. So we're starting with a minus b squared. That exponent, unfortunately, we can't just like distribute the exponent to a minus b. That would like make it a little bit faster. It means it's the whole quantity squared, so we have to take that a minus b and expand it. So a minus b times a minus b, because it's the whole thing times itself. So that's step 2, and that's just the definition of an exponent. Step 3 is to just go ahead and use the distributive property. So kind of like we did in example 1, we're going to take this a and distribute it to that second parentheses. That's what we have right here. And then we're going to take this b and distribute it to the second parentheses. It's kind of like foiling, but they're foiling in 2 steps because we're just trying to take it step by step with the proof. So then in the next step, like between 3 and 4, we'll do the second part of foiling basically. So now between step 3 and step 4, we distribute again. So we do a times a to get the a squared, a times negative b to get negative ab, and then distribute the negative b. So negative b times a is negative ba, negative b times negative b, negative times negative turns into a positive b squared. And then we want to try to simplify. So we kind of look at these two terms and notice that, like in example 1, they look really similar, but one is just backwards. So we can use the commutative property to turn this minus BA into a minus AB. We just switch the order of the factors. And then between step 5 and step 6, we can go ahead and combine like terms so that minus AB combines, or negative AB and negative AB combines into negative 2AB. Then we just bring down the a squared and bring down the b squared. So sorry these are a little bit fast. We're just kind of like showing why they work, and then we're going to apply some like kind of problem solving type things in 10.3. I just don't want to take a ton of time on the video just to kind of explain the proofs to you guys. Okay, so we proved that we started with a minus b squared and we ended up with a squared minus 2ab plus b squared. So we just kind of showed why that pattern works. Okay, so we skipped to example 4. There is an example 3, but it's the same as example 2. It's just a sum, like the sum version of the perfect square trinomial. So it's essentially the same thing. Okay, so example 4, given m plus 2 cubed, we want to prove that it simplifies to m cubed plus 6m squared plus 12m plus 8. So we're just multiplying. Like we're multiplying and we're like writing the steps that we're using to multiply. So it's a little bit more tedious of a section. So, okay, step one, we're starting with a given, so m plus 2 cubed. If it's raised to the third power for the second step using the definition of the exponent, I just have to expand it 3 times. So I do m plus 2 times m plus 2 times m plus 2, 3 times by itself. That's what cubing something is. And then now I have to like kind of distribute. This part's kind of funky, so it looks like now they're going to like one step foiling kind of. So we take, I can zoom in enough here. So what we're doing between step 2 and step 3 is we're taking this m plus 2 times m plus 2 and we're basically foiling that part. So this m plus 2 just gets copied down. And then if I were to do like m times m, that's m squared. M times 2, that's 2m. 2 times m, that's 2m here. 2 times 2, that's 4. So that's how we get that next line. And then from here, we're just combining like terms. So 2m and 2m is becoming 4m by combining like terms. And then between step 4 and step 5, we're now just using the distributive property again. So we're taking this first m and distributing it to all 3 terms in the second parentheses. So m times m squared is m cubed. M times 4m is 4m squared, m times 4 is 4m, and then now we're taking the 2 and distributing it. So 2 times m squared is 2m squared, 2 times 4m is 8m, and then 2 times 4 is plus 8. So we're getting line 5 by distributing, basically like foiling. I guess foil, like the acronym itself, doesn't really work here, but the concept is the same. And then from there, in line 5, we have some like terms. So we have 4m squared and 2m squared, and then we have 4m and 8m. So we're using the same similar, I guess, commutative property. We've used the commutative property for like multiplication. It works for addition as well, to where like we can reorder it. So we're just going to reorder the like terms together. Of course, that's not like a mandatory thing. If you can just kind of like, use different colors to group them together or underline them, whatever kind of shortcut you like to use. So basically they just take the m squareds, they put them side by side, and then the m's and put them side by side before actually combining them. So after that, we bring down the m cubed, we combine the 4m squared and 2m squared into a 6m squared, you just add the coefficients, and then 4m and 8m is 12m, and then bring down the plus 8 as well. So altogether, m to the third power plus 6m squared plus 12m plus 8. Okay, so not example, but 10.2 example 1, this is the last like kind of proof we have, so I just kind of want to get through these so that we can at least introduce like the concept of proving these. We do these all the time, we just don't like write all the statements. So, okay, so example 1, given that x to the fourth, we're given x to the fourth minus y to the fourth, we want to prove that it is equal to x minus y times x plus y times x squared plus y squared. So it's using the difference of squares pattern again. This one, they kind of shorthand a bit. They don't write all the different like distributive property, commutative property. Oh, they do write that one, but they don't write as many of like the distributive property steps in there. So it's a little bit more of a shortcut. Okay, so statement number 1, x to the fourth minus y to the fourth, that is given. And then we are going to factor that using the difference of squares. So I'm going to add a little bit inside here. So this is like the quantity that's being squared is x squared squared. Like x squared squared is equivalent to x to the fourth, and then minus y squared squared. So we have to kind of like rewrite it like that when we're using the difference of squares, so we can see like, what our a and what our b are. So this is a is x squared and then b is y squared. So difference of squares is like a squared minus b squared, and that factors into a plus b times a minus b. So we're going to use that like kind of pattern to get to step 2. So a is x squared, b is y squared. So this is my a plus b, and then this is my a minus b. So x squared plus y squared times x squared minus y squared, and then the reasoning is the difference of squares. And then again, they go ahead and this is another difference of squares, like another perfect square minus another one. So we can factor that further. This part is not a difference of squares because it's a sum, so that part just gets copied directly down. And then this is like, just my a would be x and my b would be y. So that part factors into this section. So it would be a plus b x plus y and then a minus b x minus y. And then from there, we can't factor it any more than it already is. What they do is just, we're trying to prove that it is equal to x minus y times x plus y times x squared plus y squared. They just reorder it to make sure it kind of falls in that exact same order so that it's exactly the same. So we use the commutative property of multiplication to take that x squared plus y squared and move that to the end because technically like these are all three factors, so I can reorder those factors as much as I want. And then also it looks like actually I need to put the y squared at the front as well to make it match up with what we're trying to prove. So we bump the x minus y to the front times x plus y and then times x squared plus y squared. And that's using the commutative property, just allowing you to reorder factors. Okay, so 10.3. 10.3 is all about using identities and actually kind of like solving with them or like finding values to fulfill these identities. So the one in 10.3 is about the Pythagorean theorem, and it's an identity that helps us create what's called a Pythagorean triple. So you hopefully remember Pythagorean theorem. It's something that helps you find the missing side lengths of right triangles. And the formula for it is a squared plus b squared equals c squared. And then a Pythagorean triple is like a set of three positive integers that satisfy this formula. So I don't know how much you remember from like when you actually had to use a Pythagorean theorem, but like a lot of the times you get answers that are like a radical or like an irrational number, like a decimal that goes on forever. And a Pythagorean triple is, a set of three like whole numbers that satisfy this formula, which are not always super easy to find. So we have an identity that helps us find them. So a couple of examples of a Pythagorean triple would be like 3, 4, 5. Obviously that's like the most common one, but they go up. There's technically an infinite amount because we can just keep making bigger triangles. Okay, so the identity that helps us create a Pythagorean triple, if you ever were to personally need to do that, is x squared minus y squared squared plus 2xy squared equals x squared plus y squared squared. Sounds very obnoxious to read it, but it's not too bad like actually using it. So this is a polynomial identity. X and y must be positive integers and x has to be greater than y, like the x's and y's that we put into the expression or equation. So you may notice, and they even have it color-coded, that this identity looks like a more complicated version of the Pythagorean theorem. So like this is like a quantity being squared that replaces a squared. And then this is a quantity being squared that replaces b squared. And then this is, x squared plus y squared that replaces c squared. And then all these like squareds that are outside of the parentheses in that second equation, those are just kind of a part of the formula, kind of like the Pythagorean theorem. So when we're trying to find triples, we don't necessarily need to use this whole like equation. It's just if we want to find something for a, so like the first number in our triple, we would use this. And then if we wanted to find something for B, the second number in our triple, we would use that. And then if we wanted to find something for C, the third number in our triple, we would use this. So notice like this is like always the triples have 1, 2, 3 numbers. We can find those 1, 2, 3 numbers by those three different little kind of like expressions within the equation. So example 1, it says use x equals 12 and y equals 6 and find a Pythagorean triple. So like I said, we don't have to use the full thing. If we're going to use like each part individually kind of. So if we want to find a, says that a is going to be x squared minus y squared. So that's what we'll use, x squared minus y squared. And this example is x equals 12, y equals 7, but it could be any two positive numbers as long as x is larger than y. So it could be like 10 and 9 or like 20 and 15, anything you want. X is 12, so I'll put that in there, and then y is 7, so that'll go in there, and then we'll simplify. So it'll be 12 squared minus 7 squared. 12 squared is 144. Minus 7 squared is 49. So we'll do 144 minus 49, which is 95. So 95 is going to be the first number in our triple. And then for the second number, for like our b from the Pythagorean theorem, we're going to use this 2xy expression. So 2 times x times y, and then same x and y. So x was 12, y was 7. So it'll be 2 times 12 times 7. So 2 times 12 is 24, times 7 is 168. So 168 is going to be the second number from our triple, so that's like our b. And then to find the third number from our triple, that's our c. You can see like the c is this part of the expression right here, so we'll use that, or that part of the equation, so we'll use that little expression in there. Okay, so it is x squared plus y squared, same x, same y. So x is 12, y is 7. So it'll be 12 squared, don't know why I put a 4, 12 squared plus 7 squared. 12 squared is 144, plus 7 squared is 49, and then we just need to add them together. So 144 plus 49 is 193, and that is the third number from our triple. So we found a triple. We got 95, 168, and 193. So what a Pythagorean triple is supposed to do is it's supposed to be able to satisfy the Pythagorean theorem formula, which is a squared plus b squared equals c squared. So we're just going to check it. So this is like in the order a, b, c. So 95 is going to go in for a squared, so 95, or not a squared, but just for a. So if we put 95 in for a, it'll become 95 squared. And then 168 will go in for b squared, so 168 squared. And then 193 will go in for c, so it'll be 193 squared. Notice the squared parts like stay each time. It's just a part of the formula, and we're just substituting in like a, b, and c. And then now we just want to simplify and see if the left side equals the right side. So 95 squared is 9,025. And then 168 squared is 28,224. And then 193 squared is 37,249. So 9,025 plus 28,224. If we add those together, it's 37,249, which is cool because that's what I have on the right side, so that's what it should be. So our identity worked. Okay, so this would be like the answer to what is the triple using that x and y, and then this is the check. And then example 2 is kind of like working backwards. So use the Pythagorean triple, 33, 56, and 65 to find the value of x and y. So we're trying to solve for two different variables. So if we're trying to solve for two different variables, we need to set up like a system of equations, basically. So this is I'm just going to rewrite the identity down here really quick. Sorry, it'll just take a second. So x squared minus y squared squared, and then plus 2xy squared equals x squared plus y squared squared. Okay, so we know that like this part replaces a, this is like my a squared, and then this part replaces b, this is my b squared, and then this is my c squared. And then Pythagorean triples are also written in order like a, b, and c. So this is a, this is b, and then this is c. So we can set up equations like based on that information. We could set this equal to a, and then this, just the inside of the parentheses, equal to b, and then this equal to c. And we just have to do like the inside of the parentheses because remember, like these squareds are like kind of a part of the formula. Okay, so for, like light blue equation, for lack of better terms, like the one that's based around a, it would be x squared minus y squared equals 33. And then the second one that's based around b is 2xy is equal to 56. And then the third one that is based around c is x squared plus y squared equals c, which is 65. So we have our like three equations. Anytime we have three equations, well, we really only need two equations to solve for two variables, but we have three, so I guess we have an extra one. You want to pick like two equations out of this though, like whichever two will help you like solve for a variable more easily. So this goes back to like Algebra 1 when you're solving systems of equations. So the ones that pop out to me are these two, because they both look very similar, and one has like a y squared and one has a negative y squared, so we could probably use elimination with those two variables so that we can solve for x. So I'm going to rewrite just those, or sorry, with those two equations, I'm going to rewrite those two equations and see how it looks like stacked on top of each other. So x squared minus y squared equals 33, and then x squared plus y squared equals 65. And then now, because like these are the same term but they're opposite signs, I can just like add the two equations together, and that's called elimination. Like we're using the elimination method of solving systems to eliminate the y squared terms and be able to solve for x. Because if I add those two together, a negative y squared plus y squared would cancel out. So we just go left to right. So like x squared plus x squared would become a 2x squared. You just add the coefficients and the powers stay the same. And then negative y squared plus y squared would cancel out because it's the same term, just one is positive, one is negative. And we break down the equal sign. And then 33 plus 65, we add those two together is 98. And then now we have a one variable equation that we can solve. So I just want to get x by itself. So I would divide both sides by 2 to get rid of the coefficient. 2 divided by 2 cancels out, and then I'm left with x squared equals 49 divided by 2 is, 98 divided by 2 is 49. And then now I can square root both sides. So I end up with x equals, we're solving, so I would get x equals like positive or negative 7 technically. But remember that like with, gotta go way up here, with the like identity itself, x and y need to be positive integers, so the negative 7 wouldn't really be like valid here. So we would just use x equals 7. So we need to find x and y. We found x equals 7, and then now you can just pick any of the three equations to solve for y. Probably the middle one, like the green one right here, is the easiest to use, but you could pick any of the three. So I'm going to pick that one that's highlighted in green, so that's 2xy equals 65. And then we just found that x was 7, so I'll put 7 in for x, so it'd be 2 times 7 times y equals 65. Oh no, hold on, sorry, I mixed up my numbers. I like kind of mixed up the two equations. It's supposed to be a 56. So just in case I'm messing it up, I'm plugging into this equation, which is 2xy equals 56. I accidentally put 65 because I looked at that bottom equation. So 2xy equals 56, and then that x equals 7 is going in for x. So then I have 2 times 7 times y equals 56. 2 times 7 is 14, y equals 56, and then I'm trying to solve for y, so I have to divide both sides by 14. So 56 divided by 14 is 4. So I end up with y equals 4. And then I have my two values for x and y. So x equals 7, and then y equals 4.